Ohayou gozaimasu.
Good morning and welcome to GTC Japan and Graphics Technology Conference, GPU Technology Conference in Tokyo. And I always love coming here to speak because there's such enthusiasm for technology. I really feel at home, like you embrace everything we do. So thank you for welcoming me here. The GPU Technology Conference was born by the invention of CUDA and the invention of GPU computing. And we're really inspired by the fact that graphics is more than just a pipeline. Graphics is computational, and visual computing is broader than just making pictures. You start with physical simulations, parallel computation, and a lot of math and a lot of understanding. And you build the pictures and you build solutions along with the pictures. GPU computing has experienced exponential growth. CUDA is the realization of two kinds of computer processors working together. The CPU is a high-speed, serial, single-threaded processor, low latency, can process a small amount of information very quickly. The GPU is a highly parallel, high-throughput processor, many threads, many pieces of data, lots of things happening at the same time. So the marriage of these two kinds of processors enabled by the CUDA programming environment allows us to achieve many exciting and interesting things. GTC Japan has been growing and evolving. The first GTC Japan in 2010 had just under 500 attendees. Today, I think we have more than 1,500, actually over 1,600 registrations, and maybe we'll have even more attendees than that. The mix of attendees and participation has changed over time. We have now very broad industry participation, a lot of different companies contributing, sponsoring, and attending. And the kind of applications and the kind of problems that we look at have changed through the course of multiple GTCs. Today we will talk quite a bit about computer vision, using machines to recognize and analyze things, as well as machine learning, teaching computers to understand, analyze, and extract information from images and other data. As we have an explosion of imagery and other data that is being captured and uploaded to the internet, we have to figure out what to do with it, analyze it, and it's just too much raw data for people to analyze, so we need to have the machines help us. Since its introduction, CUDA has really blossomed and expanded, and we say CUDA everywhere, and we mean it. We want CUDA on every kind of device, from embedded devices in vehicles and other kind of objects, phones, tablets, computers, supercomputers, every place. We have over 500 million CUDA-enabled GPUs that have been shipped. A very large number of CUDA downloads, which indicates the size of the developer community. We teach CUDA in parallel programming courses worldwide. Probably by the end of this year, early next year, we'll be close to 1,000 university courses teaching CUDA. And that leads to new applications. new exciting ways of using GPU computing, academic papers, research, and real products, real technology that makes use of CUDA. So I'll just highlight a few examples of things that have been done that we think are particularly interesting. There's a company called Rescue, I believe they're in Australia, that has been exploring using GPU computing to enhance the capability of drones or unmanned aerial vehicles. Onboard GPUs are used to do navigation and collision detection, so that you can have more drones up in the air looking for forest fires and doing surveillance for people's safety without colliding with the other drones that are in the air at the same time. At University of Illinois, on the Blue Waters supercomputer, there were over 3,000 GPUs applied to the problem of simulating the capsid of the HIV/AIDS virus to try and understand the infection mechanism and be able to potentially defeat it. If you can understand how the capsid works, you can prevent it from being allowed into the cells and infecting cells. That simulation involved simulating over 3 million atoms in the molecule. I think it's a truly amazing achievement. Another company, Hologic, is using GPU computing to do 3D reconstruction of imaging data for breast imaging to do a better job than simply using X-rays for identifying a disease or tumor tissue. So that this results in much lower radiation doses and much better quality detection and much better quality healthcare. The GPUs are changing people's lives in all these ways. Closer to home, work that's going on in Japan, Tokyo Institute of Technology. There is a project that is using parallel GPU computing to identify substrings or k-mers in DNA sequences to try and determine the frequency of particular patterns. And this can be done much more efficiently with GPUs and CUDA. At Waseda University, they're using GPUs to teach robots how to select appropriate behaviors. They use a deep neural network and use GPUs to train the network and to figure out grasping motions, how the robot should behave. Hokkaido University has a project where they use parallel finite element model simulation to simulate the deformation and fracture or tearing of soft biological tissue, to simulate surgery and provide training, haptic feedback for new surgeons to be able to learn how to do surgery without actually cutting real flesh. So these are very exciting applications, and these are examples of GPUs really changing what we're able to do. One recent announcement at the International Supercomputing Conference a couple weeks ago shows the reach of GPU computing. Several companies have announced that they're going to build ARM64 based servers for high performance computing. And this is really significant because traditionally other CPUs have been used as the core processors for high performance computing. And ARM64 is a much more lightweight kind of CPU architecture, much more power efficient than some of the processors that have been used before. But by itself, ARM64 would not be sufficiently powerful as far as computing to really build a supercomputer. But the combination of CUDA with GPU computing combined with ARM64 CPUs provides an excellent power efficient substrate for building next generation of high performance computing. It's certainly not the only way to build these, but it's a new innovation, it's a new approach to building high efficiency, high performance computers. Other approaches to power efficient supercomputing. The Green 500 measures the most power efficient implementations for supercomputers, and all of the top 15 winners in the last round that was announced have NVIDIA GPUs in them. In fact, they have Kepler architecture GPUs. And again, number one is very close to home. The Tsubame KFC supercomputer, which is at Tokyo Institute of Technology. I just found out yesterday that KFC stands for Kepler Fluid Cooling, not the Kentucky deep fried chicken that you might associate with KFC. But the name is appropriate because it is the processors are immersed in oil to manage the thermal cooling for the computer. So the processors run at a very reasonable, much lower temperature than in an air-cooled or water-cooled system, and so you get more power efficiency. I think it's a really great machine, and maybe the wave of the future for supercomputing. We may see a lot more oil-cooled systems. So the other implication of Kepler, besides moving up the computing food chain into supercomputing, Kepler has also moved down into our mobile architecture. You may or may not know, historically, our mobile architecture, the Tegra family of processors, had a different graphics pipeline than our GPUs for desktop and high-performance computing and laptop. The progression of architectures for the desktop, from Tesla to Fermi to Kepler and on to Maxwell, is our fully capable, fully functional, does all of graphics, does all of computational graphics, supports CUDA. With the introduction of our Tegra K1 mobile processor, we've now unified our architectures. So going forward, we'll be building a single graphics architecture which spans the full gamut from mobile and embedded architecture all the way up to HPC. And what that really means is that all the capabilities from programmable graphics, visual computing, all the way up to CUDA and programmable parallel computing are available from embedded architectures to be deployed and developed all the way up to very high end. So now I'd like to demonstrate the truly awesome power of Tegra K1.